Hello everyone, so this is an update on my battery management system. The balancers are now finished, so there'll be two versions released, one for lithium ion and one for LiFePO 4. They'll just have different voltage set points on them for the relevant chemistries. So this entire system is designed for safety, accuracy, reliability and longevity, and it uses analog electronics completely. So the system in the power off condition consumes absolutely no power whatsoever, so when you're not using your battery bank you don't have to unplug anything at all. You just power it off and that's it. It's consuming nothing at all, so it's not going to destroy your battery. So I'm going to switch it on now. So this is also automatically connected the charger too. One of the commenters commented about the LED brightness. They're too bright, and I agree. That's just because I was using the recommended resistors from an LED resistor calculator, which were about 470 ohms. So I'm going to have to make those resistors about 4 kilo ohms to make the LEDs sort of dimmer and easier to look at. So this is the next part of the system which I'm working on, and this is the main board which handles the overvoltage, undervoltage and balancing signals which come from the cell protection modules. Now this board isn't strictly necessary. You could just use these modules on their own and just have balancing, or design your own system for handling this, but I thought I would design a nice simple product to give the user more options anyway. And this uses Panasonic relays, tantalum capacitors. There's no really any sort of perishables in this system, apart from maybe the relays. They'll probably wear out after many years, so you may have to watch with those. But the sad fact of life is everything wears out eventually. So the original intention of this board was that it would be directly connected to the battery voltage, and it had have a voltage converter on it. So this one had a linear regulator on it which would take 9 to 30 volts in and then output 5 volts. But that was just a total fail because the regulator just got roasting pretty quickly. So it's going to be up to the user to power this. So I'm just using one of these buck converter modules to put 5 volts into the board. So when I finally release this, the 5 volts will go in and it will just go through a polyfuse and a capacitor, and it comes out there. Because to get these modules to switch on, you need to supply 5 volts into their isolated interface to get them to switch on. That's essential. And then you've got your signals coming out which you can do what you like with, or connect them up to the product I've provided. Okay, so this LED which is starting to flicker here, that's a balancing signal coming off the modules. So one of the modules is about to start balancing the battery, well, one or more. So but you cannot actually see the green LEDs coming on yet, and that's because this balancing signal actually comes on 1 millivolt before the actual balancing triggers. That wasn't intended, that's just some quirk of the design, but I thought that might actually be helpful. So when your battery the voltage is rising during the charging process, you'll get the balancing signal coming out, and then the actual balancing will begin just a millivolt later. So it's not really that much of a difference really. And this balancing signal, it's sort of a high frequency signal. There's not really any hysteresis on it. So as you saw the LED getting brighter, that would probably be quite a noisy signal, fluctuating quite rapidly between being off and being at like just under 5 volts. So the customers, that if they want to use that signal, they can probably run it through an LC filter and find a way to connect it into the current limiting circuitry on their charger, and then the charger could be ramping down the current whenever it detects that signal. Basically just so the balancers on this don't have to waste as much power. But on a healthy battery anyway, these balancers will always be able to keep up. And in most normal cases, you'll not actually need to use that balancing signal for anything. The only thing this board does with the balancing signal is just use it to light up that LED there. So what the customer would normally be expected to do is just set their charger to a multiple of whatever balance voltage is set per cell. So say you have a 10 cell pack, 10 cells in series, and you want them to be charged to 4.1 volt per cell. So you set the balance voltage to 4.1 per cell, and then your charger to a multiple of that. So you set your charger to 41 volts, and that's going to ramp off the current anyway. But this would be good to use if, like, you maybe got something that's just built out of crappy laptop batteries which keeps going out of balance. And that means your charger can actually help the balancers by ramping down the current earlier. So on the lithium ion version, the overcharge detection voltage I've set at 4.21 volts, because I don't expect the customer to be charging their batteries right up to 4.2 volts, because this system's designed for battery longevity, and like solar power or large electric vehicle packs. So the customer, I would expect them to be setting their balance voltage no higher than 4.15 per cell, so that you've got that safety headroom. Because if something goes wrong with the charger and it just keeps charging and charging, your batteries start hitting 4.21, the signal will get sent, the relay will cut off the charger, and it will not come back on again unless power is reset and there's no overvoltage signal present. So it's a really safe system. And here's just an example of what they look like when they're balancing. So whenever that green LED is on, that means that power has been discharged into the resistor. So it's a good visual indicator. Now it seems to be within the range of 5 millivolts. So if the battery voltage goes 5 millivolts over the set point, the set balance voltage, the LED will be fully on. It sort of like seems to go on some sort of duty cycle. But when it's just teetering at the brink of the balance voltage you set, it'll just sort of flash intermittently. But it's within some sort of 5 millivolt range. It's also worth mentioning that this system, provided the customer does adjust the balance voltage properly on each module, it can balance to within a millivolt, so it's very accurate. Also, in regards to these balancers, there is the option to add an extra resistor, because the holes for the resistors to go into are slotted. So when these are fully on, they balance at about 1 amp. So the MOSFETs in these are powerful enough to take 2 amps no problem. So instead of a 3.9 ohm resistor, you'd use one of maybe a slightly lower value, or what I would prefer is an extra resistor just connected in parallel, just in case one resistor fails, which is probably very, very unlikely, to be fair. So further words of advice before I actually start doing the overcharge test is how to connect these up. So I'll just demonstrate using an older version of the product. Basically this is the opto-isolated interface here, so just try and focus on that a bit better. So you've got your over voltage under voltage balance and ground in 5 volts. So I could supply the pin header, but what I would prefer is that the customer just solders the wires directly into the holes in the board, and that way it's a much more secure connection. Because you want these connections to be secure, otherwise there's a possibility that the over voltage and over discharge protection might not actually work if you've got a bad connection. But what I've done here is, as you can see, I've just got them all soldered together in parallel, and it's just a socket that you could pull out. Okay, so now I'm going to demonstrate what happens when a cell goes over voltage. So as I said, when this is in the power off condition, none of these relays are connected, so the relays switch on as soon as this board's powered up. So that's charger connected now, and just shortly we'll see the balancing LED coming on, because I've turned the balance voltage up as high as it can go, and hopefully we should get it triggering soon. Well, the camera for some odd reason never even recorded the over voltage test, so I'll just tell you what happens. As the module starts reporting an over voltage, you'll see that the red LED on one of the modules getting brighter and brighter over about 3 to 5 millivolts, and once it gets close to full brightness, the signal is then of a sufficient duty cycle for this to pick it up and then just trigger the relevant relay, and it stays triggered and it stays off until you reset it. So I'm just going to have to demonstrate it this way. So we'll pretend that there's an over voltage, and that means that the charger LED comes on, the warning, the relay turns off, and it stays off. It cannot be reset unless you reset power going to this module, so it's very safe. Due to like variations in due to like the tolerances of the voltage references and the resistors, the over voltage cutoff could actually trigger as low as 4.18 volts in this design. That's still fine, because I'd only expect people to be charged their batteries up to 4.1 per cell anyway, so it's still plenty headroom for the modules to balance.